can start. So today is a very important topic known as Bch Code, Bose, Chaudhary and Hockingham Code. So it's good that it was like discovered by Indian people. Okay, so definitely discovered it. So these codes are basically mother of all good codes. So they are the generalization of the Hamming code. So let me show you 1 minute. Okay, so here's the thing. BCH, they are very important codes. So I should write first name Bose Ray Chaudhary and Hockingham. So B from here, C from here, and H from here. BCH codes. Okay, so in order to construct BCH codes, the idea is really very simple. Look at the Hamming code. The Hamming code we know. So start with cyclic Hamming code. So what we do, we need to take Gx, a primitive polynomial of degree m over Gf2, right? So basically we are looking at Gf2 slash Gx. We know that this is a field of order 2 raised power m. If alpha is a root of Gx, then we can form the elements as 0, 1, alpha, alpha square, and so on, alpha raised power 2 raised power m minus 2. Now, if you recall, we could have, so we can construct the parity check matrix H of the Hamming code as binary expansion of these elements 1, alpha, alpha square, dot, alpha raised power 2 raised power m minus 2. So we can use 2 raised power m minus 1 non-zero element. Zero is not part of it because we need to look at all. We need to construct this matrix such that no two columns are multiple of each other. So these are m tuples. The length of each one is m tuple. Let me give you an example also so that it is clear. So C is a code. C with parity check matrix. H is a Hamming code, right? if you take m is equal to 4, then length will be 15, and our parity check matrix will be H will be 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 and 1 1 0 0 1 1 0 1 1 1 1 0 and finally all 1. This is the parity check matrix of this Hamming code. So binary expansion of all the elements. So this is equivalent to, we can write down all the elements, because m is equal to 4, so we are looking at field with 16 number of elements, right? So we are looking at GF16. So elements are 1 2 3 4 5 6 and so on, 14 15. So we are just writing the binary expansion of these, right? This is the parity check matrix, right? Another example for GF8. Suppose Gx is x cube plus x plus 1. So GF2 x modulo Gx is GF8 field with number of elements. So we will have 0 1 alpha square alpha cube is equal to alpha plus 1, alpha raised to power 4 is equal to alpha square plus alpha, right? Alpha raised to power 5 is equal to alpha square plus alpha plus 1, and alpha raised to power 6 is equal to alpha square plus 1. These are the elements. So H will be 1 0 0 0 1 0 0 0 1 1 1 0 0 1 1 1 1 1 1 0 1. So these are 1 alpha square and so on, alpha raised to power 5, alpha raised to power 6, the extensions, right? So this is for GF8. When we are looking at GF16, of course, we need a working polynomial x raised to power 4 plus x plus 1 is our GX. Right, so this is GF16. So I think when we are dealing with the having code of length 15, we need to worry about the field with 16 number of elements. This is very, very important. So now let us see what to do. Okay, so we start with the parity check matrix. So we are looking at m is equal to 4, n is equal to 15, field is GF16, our working polymer is x raised to power 4 plus x plus 1. So we need to have a table of GF16 with us, right? So n is basically, we know that 2 raised to power m minus 1, right? So that's why it is 15. So now we consider the parity check matrix with columns arranged in decimal order. So as we considered it earlier, 1, 2, 3, 4, 5, and so on up to 15, right? We can write down the binary expansion of this of length 4, right? So each binary expansion is an element of GF16, right? Except 0 here. So now, now the question is, we know that uh, this code, which is coming from this parity check matrix, can, right? We know that it can correct, Hamming code can correct singular. The distance is 3. So the question that Bose and Chaudhary asked, can I add more rows here so that we can correct 2 errors or 3 errors? If I want to correct 3 errors, how many rows should I add? Or if I want to correct any number of errors, T errors, how many rows should we add? Okay, this is a very general question they ask. So I'll show you first the construction for distance. When you can correct you want to correct 2 errors. So add 4 more rows here. So basically, our new parity check matrix is 1, 2, 3, 4, 5, 14, 15. Right, this is our actual parity check matrix. And now we are going to add some function f of 1, f of 2, f of 3, f of 4, f of 5, so on, f of 14, f of 15. So what I have done, so these are some arrangements of columns of GF16 which we don't know. So that's why I've written functions, some functions of these things. So now we have added 4 more rows, and we want to make sure that we can correct 2 errors using this parity check matrix. Okay, so that means actually make sure that we can correct 2 errors, and then we'll see. So we don't know these values of FIs. So the question is how to choose FI. FI. How to choose FI? This is a question, So keeping in mind that we are dealing with GF16, all these elements 1, 2, 3, 4, 15 is the element of GF16, and f of 1, f of 2, f of 3, f of 4, f of 15 are also elements of GF16. These are 4 tuples, vectors. So now suppose two errors have occurred. Okay, suppose 2 errors have occurred, and we can also assume that they occurred at certain positions. So suppose occurred in position I and J, 2 positions at I and J. So these are 1 to 15. So ith position and jth position, somewhere errors have occurred. So now in that case, syndrome will be what? Syndrome S will be what? Syndrome, we know, if X is a sent vector, Y is a received vector, we compute the syndrome of Y. The syndrome of received vector will be what? basically sum of the columns where the errors occurred. So syndrome will be hi plus hj, right? Some of those columns, you know. So that means we have, and here the syndrome will be S1, S2, I would say. So S1, S2 will be I plus j and f of I plus f of j. Right? This is our syndrome. That means syndrome is known. So S1 and S2 is known. I and j is known because these are the positions where the errors occurred. We don't know what is f of I, f of j. So actually we get equations that S1 is equal to I plus j and S2 is equal to f of I plus f of j. Okay. Syndrome is some of the known result. We have added those two columns, ith column of this petri check matrix and jth column of the petri check matrix. So actually we are getting this. So S1 and S2 are known, I and j are known. Only f we don't know, right? So the question is how to find f so that we can solve these equations, you know. So one try, you know, one case could be when we take, say, okay, fi is same as I. Suppose say we take the same thing, right? If I take fi is equal to I can solve for I and j at which positions error occur, right? So now if I take fi is equal to I, so equations will be s1 is equal to I plus j and s2 is equal to I plus j. Now this is inconsistent, right? So we, you know, it doesn't work. So we will not be able to solve for I and j. So this is not going to work, right? Second case, A could be f of I is equal to I square. Is this a possibility? I'm just trying, you know. Now in this case, we know that S2 will be I plus j whole square, right? Same thing as, you know, I square. Actually, it was I square plus j square, which is same thing as I plus j whole square, right? So this is nothing but S1 square. So again, we will not able to find no unique solution in GF16. These equations are over GF16 that you need to remember. All these elements are elements of GF16, right? So there is no solution. We cannot solve. Third thing we try, can I solve it using Fi is equal to I cube? Okay. So in this case, let's take some. So now we are trying. So when we take Fi is equal to I cube, so one equation is I plus j is equal to S1. Second equation will be I cube plus j cube implies that S2 can be written as I plus j. I can factor it I square plus ij plus j square, right? So this is nothing but S1 times S1 square plus ij. This implies that I can find out the value of the product of two I and j. S2 by S1 plus S1 square, right? So now we know the sum I plus j, that I plus j is equal to S1 and I into j is equal to this S1 and S2 are known to us because we computed the syndrome, right? The first component of the syndrome is S1 and second component of the syndrome is S2. It's a column vector S1, S2, right? So now I and J are the error positions, so how do we find that? So basically I and J are roots of the equation. I can say that it is known as lambda x plus I into x plus j. If I form this polynomial, okay, so this is x square plus s1x plus s2 divided by s1 plus s1 square. So this is known as error locator polynomial. Okay, this is very important polynomial. So as soon as errors occurs at certain positions I and j, which we want to know at which position error have occurred, we compute this because syndrome we compute. Once we compute the syndrome, we know the value of S1, S2. So we know the value of this error locator polynomial. We solve it and we get the values of I and j. And and then it's very easy, to actually decode, then it's very easy to decode. Okay, so the error positions, you just flip them, right? Those positions. So let me show you the decoding procedure now. Decoding procedure. First thing is step 1. Step 2. Find the roots of the error locator polynomial. So since we compute the syndromes, so we know the value S1 and S2, right? We know the S1, we know the S2. And syndrome is basically sum of the column positions, so find the roots of the error locator polynomial. And step 3, flip the bits in the error positions. Right, so 8th and jth position, so X is set.
So from error locator polynomial, what we get?
From error locator polynomial, we will get the positions where the error occurred. So we will know I and j.
Yes. Okay.
Right. So we know. So X is sent, Y is received. We compute the syndrome. Okay. And we know that 2 errors have occurred. We don't know where. We know 2 errors have occurred, right? So syndrome is computed. So S1 and S2 is known to us. So we compute the syndrome. Okay. And then, so once we solve the error locator polynomial, we know I and j, that error occurred at position I and error occurred at position j, right? So we just flip those bits in y, so we will get x, right? Got it? So if x is x, right, and y is received, y is equal to y1, say this is yi, yj somewhere, and yn, right? So once we compute the syndrome, we compute the syndrome, so we know the value of s1 and s2. We know s1 and s2. Find the just s1 and s2 is known. So from this we can find the error locator polynomial. Once we know the error locator polynomial, so we can solve it for, then we know the values of I and j. So we know that error occurred at this position. Once we know the value of I and j, you just flip this bit. So if it is 0, I will make it 1, right? If it is 1, I'll make it 0. Just flip it, whatever the value it is. If 1, we convert it to 0. If 0, we convert it to 1. And we get the X. Because those are the positions where error occurred. Okay. So now there are certain observations. First, if there are no errors, so in that case, we know that S1 is equal to S2 is equal to 0. Syndrome will be 0, right? There is no error, right? Second, if there is one error at position I, okay, then S2 is I cube is equal to S1 cube. Okay. Okay. So if there is one error at position I, then S1 is not equal to 0. I mean, actually, because then only we will know that error is occurred. If S1 is 0, so S2 will be 0. So actually, in that case, S2 is equal to S1 cube. So one error at position I. Okay. If S1 is not equal to 0 and S2 is not equal to S1, then we solve for the roots of the error locator polynomial. Okay. So I think let me summarize it in the next page. Yeah. So basically, calculate the syndrome. Okay. S1 and S2. Right. So first, if S1 is equal to S2 is equal to 0, no error. Right. Second, if S1 is not equal to 0 and S2 is equal to S1 cube, one error at position I. But this may also happen, right? That there is only one error. Third case, if S1 is not equal to 0 and S2 is not equal to S1 cube, solve for the roots of the error locator polynomial. Okay. Now there could be cases. There are two distinct roots. Roots I and j, right? Roots I and correct the errors at those positions. At these locations. Right. And if no roots, when you solve the equation, suppose there are no roots. One root, that is also a possibility. One root or double root. Do nothing. That means as more than two errors have occurred, more than two errors have been detected. Okay, so this is the thing. So essentially, either there is no error, there is one error at one position I, or there are two distinct errors at positions I and J. Fourth case, more errors, has been detected. And actually, finally, if S1 is equal to 0 and S2 is not equal to 0, again, more than two errors, so we can ignore basically. So this is the key idea of the decoding procedure. This is a summary. Okay, how do we compute the syndrome and how do we actually decode? Now, so in general, so whatever we have done, so I can write down now the parity check matrix in a most general form. 1 alpha square alpha cube. Remember, in the most general form will be alpha raised to 2 raised to m minus 2, right? And f of 1, we know that this is our I, right? So f of I is I cube, if you remember. This is the solution that worked, right? F of I is equal to I cube. So means we are going to do the cube here. So 1 cube is 1. Alpha cube will be alpha cube. Alpha raised to power 6, alpha raised to power 9, alpha raised to power 12, and so on. Alpha raised just done the cube. This is our paired check matrix for correcting two errors. Okay, and this is a basically binary Bch code. So double error correcting. That is how we construct it. So in particular, for our GF16 example, H will be 1 alpha square alpha cube alpha raised to power 14, and cube will be 1 alpha cube alpha raised to power 6 alpha raised to power 9 alpha raised to power 12, and then it repeats actually. Finally, we have up to alpha raised to power 12. This is our GF16. So okay, so now that means I can write down the binary expansion of each of them. So we will get a bigger matrix. Let me show you if I have a picture here. Okay, so that's all.
So this parity check matrix is for polynomial x raised to the power 4 plus x plus 1? Or
Correct. We have used the x raised to power 4 plus x plus 1.
okay.
So this all these four tuples, we are getting from this GF16 only. It's really interesting to see how constructed, The idea is very simple. Okay. Now I think one thing that I would like to find here. So now we know that so this H is given to us. Okay, one. Okay. So the idea is really simple. So the key idea is you take the parity check matrix, finally cyclic Hamming code, right? Add more rows, and once you add rows, solve for those things, right? And you will get the idea. So actually, this is how it was discovered. Nowadays, actually, they taught it in a different way. So by minimal polymers, I'm going to tell you now that about minimal polymers. So that means it's really easy to construct Bc codes. And one very important property that because it is, I would say that it is very favorite to engineers, because you want a setup where you want to correct say 15 errors. So T is equal to 15. So you know how many rows you need to add actually, right? In other words, we can do it from generator polynomial. So we know how to actually construct that. That is in our hand actually, right? So that is really very, very important. So now actually I just want to tell you one very important thing in terms of minimal polynomials. Now a code word must satisfy, if X is a code word, we know that Hx transpose is equal to 0, right? If H is a parity check matrix. So in terms of, when we take the parity check matrix actually, and we take C as equal to C1, C2, Cn is a code word, actually this will tell us that since we are having two parts, one is this portion at the top, one alpha square, alpha s power 14, another one is cube. So basically we can get C alpha is, suppose C alpha is a code word, so alpha is a root. So this implies that C alpha will be 0, right? By the definition, and C alpha cube will be 0, right? Okay. So therefore, generator polynomial X will be minimal polynomial of alpha, which is M1X, times minimal polynomial of alpha cube, which is M3X. This is how you get, the minimal polynomial of actual code that we have constructed. Okay. So this is a really very basic thing. So actually now I'll give you example here. The parameters of the Bch code, double error correcting Bch code is 2 raised to power m minus 1, that is length. 2 raised to power m minus 1 minus 2m, because we added, certain number of rows, right? So m was there, m rows were there initially, we added m more rows, so 2m rows are there, right? And actually the length is 2 raised to power m minus 1, so n minus k. We get, this is our, using that, we can get, this is the dimension, and the minimum distance is 5 by design. This is by design, okay? So 5 means it can correct 2 errors. You can correct 2 errors. So actually, again, I'll just show you in the specific example that we took. M is equal to 4, N is equal to 15, and K is equal to 7, D is equal to 5. We have 15, 7, 5 Bch code, right? So M1X is x raised to power 4 plus x plus 1, okay? M3X is x raised to power 4 plus x cube plus x square plus x plus 1, right? And Gx is M1X into M3X, which is x raised to power 8 plus x raised to power 7. I mean, you can do the calculations. I'm not doing all the calculations, just writing it directly. X raised to power 4 plus 1. Okay. So let me show you now, finally, how the decoding is done. Okay. So let me show you the finally. So this is our code. Okay. So suppose received vector is 1101111011000. Suppose this is our received vector. Yes.
How we get M3X?
Just M3 is the minimal polynomial, right? From here, and the minimal polynomial of alpha cube. Alpha cube. Okay, so we know how to get the minimal polynomials, right? You remember? By the factorization, you remember?
Yes.
The previous classes, so it's just a minimal polynomial of alpha cube we are writing. That's all.
Okay.
So suppose the received vector is this, okay? And so the syndrome will be you remember S1, S2 will be receive vector of alpha and receive vector of alpha q. Okay. So you remember, I think we have shown in one class that if cyclic code is there, okay. So how do we get the receive vector? If you just take modulo or GM, modulo operation, so you will get the R of alpha, which is the syndrome. So in this case, difference that we are taking two, R of alpha and R of alpha cube, syndrome. Okay. Now this I can compute. So from here, if you compute R of alpha, if you take this as a vector and write down as a polynomial and compute R of alpha, this turns out to be alpha raised to power 11. Actually, I'm just not, you can actually compute this, and this portion is alpha raised to power 5. Everything is in GF16. You have to keep that thing in mind. Okay, you need to do that arithmetic quite frequently. So this implies that error locator polynomial lambda x is x square plus alpha raised to 11x plus 1, right? I've just computed S1. S1 is here alpha raised to power 11 and S2 is alpha raised to power 5. And you remember we have these calculations here. I have substituted everything here, the value of S1 here and this expression, S2 by S1 plus S1 is square, and you compute everything in GF16, so you know how to compute everything in that field. Okay, so the result is x square plus alpha raised to 11, which is S1 times x plus this quantity turns out to be 1. You have to simplify it. Okay, now you factor it, it turns out that this is x plus alpha raised to power 7 into x plus alpha raised to power 8. You can factor it. You can see that because alpha raised to power 15 is 1, right? So alpha raised to power 7 into alpha raised to power 8 is alpha raised to power 15, which is 1 in GF16, right? So you can just factor normally. These are the factors. So the roots are alpha raised to power 7 and alpha raised to power 8. Okay. So when these are the roots, 1 minute. Roots are this. So we know that if R is R vector 0, 1, 0, 1, 1, 0, 0, 0. Okay. So error vector, because we know what is the positions where the roots are. So these positions alpha is for 7, alpha is for 8, 7th. So 1, 2, 3. Basically, 3, 1, 1. This is for alpha is for 7. This is for alpha is for 8, right? So these are the positions where error occurred. We just flip those positions. So actual vector, received vector x will be 1, 1, 0, 1, 1, 1, 1, and 0, 0, 1, 1, 0, 0. Got it? So wherever the errors occurred, those positions we flip, receive vector, and we be able to decode. Actually, these two positions will be there. Right. So we flip those positions and we get the received vector. So this is how the decoding is done actually, So I guess I'll give you one example which you can do it as an exercise. Suppose received vector is 1, one. Okay, n is 15, and we are in ZF16. So the seed vector will be, the seed polynomial will be 1 plus x raised to power 8. Okay, syndrome. So I think if this is the thing, you just decode it actually, You can find out what is error locator polynomial, lambda x, and so on. Okay, just do this. Compute syndrome. And decode it. Okay, so I think I leave it as an exercise for you. So for the double error correcting BCH code. So I think that's all for today. In fact, I just mentioned that. So in general, now what happens? This was, we talked about double error correcting BCH code. So when we want to correct two errors, how do we handle the things? So if we want to correct three errors, we need to add additional m rows, right? So there will be 3m rows total in the petri check matrix. If you want to correct 4 errors, there will be 4 times m rows, So essentially, in general, what we need to do, there is alpha raised to power I is a typical element, f of alpha raised to power I, and then, or you say some function f1, some function alpha f2 of alpha raised to power. This is how we keep on extending the idea. And generator polynomial will be m1x, m3x, and so on. We can just keep on doing it. So each fi is chosen in appropriate manner so that we can correct. So if you want to correct two errors, we have to choose f1 and f2 in appropriate manner, right? So this is the idea through which we can extend the things. We'll talk about more the general case in the next class. So I think this is the key idea about double error correcting BCH code. I hope you got the idea. So starting from the binary cyclic Hamming code, we extended it to double error correcting BCH code. And it's a really nice idea because now as an engineer, I have control. If I want to correct two errors, I can add m extra rows in the petri check matrix of the Hamming code. If I want to correct three errors, I'm going to add 2m extra rows in the petri check matrix. If I like that, we can keep on continuing. In general, I have a choice. If I want to correct t errors, I know which BCH code I need to choose, right? So it's a t is kind of design distance. It's in our hand. How many errors we want to correct. Accordingly, we can do the calculations. Okay. So this is the key idea. I hope you got the basic idea about the binary binary Hamming code. Binary BCH code. And in the next class, we'll give you some general ideas about the BCH code, how we can handle the minimal polynomial business. So that's all. Do you have any question? Any question?